And now we get to continue our discussion about IP networking by talking about an introduction to CIDR. CIDR is classless interdomain routing and is used instead of classful routing. Now, classful routing, if you recall, has to do with using classes such as class A, classes A, B, or C, because, well, it turns out that the classes were pretty much inefficient. As you looked around, you realized that those networks were either way, way too big or way, way too small. For instance, let's say I had a company and I needed 1,000 IP addresses. Well, I look at my possibilities. I have an option to get a Class C address with 256 addresses. I have an option to get a Class B with 65,000 addresses, or a Class A with 16.7 million. And ultimately, well, 1,000 just didn't fit into any one of those. Pretty much my only option at that case is to get, well, 4 Class Cs. Which, again, is still not very efficient. There's got to be a better way to be able to handle this. So not only were the sizes either too big or too small, but there just weren't a whole lot of them. If you remember Class A, there was only 127 of these guys. So maybe larger organizations such as Microsoft's and Apple's and nations out there may fall into needing a Class A, but there's only 127 of them, which means you're going to run out pretty quick. And then same with Class B, it was still very limited. And then Class C, there's still a lot of them, but we're still fairly limited, especially if this guy right here needs 4 of them. So classful routing, there was a lot of issues found with it. It was very easy to implement, very inexpensive for the compute cycles that were necessary for the routers, but wasn't necessarily ideal. So we started moving over to what's called classless routing. Now, in order to talk about classless routing, we need to talk about a subnet mask. Briefly, a subnet mask is used to determine if an address is on the same network. By the way, that is the perfect answer if somebody asks you in a job interview. What is the purpose of a subnet mask? It's used to determine if a target address is on the same network as me. But what exactly does it do? Well, it separates an IP address into a network and into a host. Now remember, when we had the Class A, the Class B, and the Class C networks, the separation was automatic. I knew if this was a Class A network, the first octet of my address was part of the network. The other 3 octets of my address were hosts. So if I saw a Class A network such as 8.4.7.12 randomly created address, Class A, I could just draw a line right there and say, okay, the 8 here is my network and everything else is a host. Well, the subnet mask does the same thing. And what it does is it uses a process called binary ANDing. It says this and this. So 1 and 1 equals 1. 1 and 1 equals 1. 1 and 0 equals 0. 0 and 1 equals 0. And then 0 and 0 equals 0. So the only way to get 1 at the a 1 here as an answer is to have both 1 and 1. So we have an example here. We have an address 192.168.15.42 and a network mask of 255.255.255.0. And I converted those into binary for us here. The first line 192.168.15.0, and then right below that we have 255.255.255.0. Now if we look at the network mask, when we convert it into binary, we notice this line right here is pretty much the separation of our 1s and our zeros for our mask. With a subnet mask, anywhere that there is a 1 is a network. Anywhere that there is a 0 is a host. So by doing this binary ANDing, 1 and 1 equals 1, 1 and 1 equals 1, 0 and 1 equals 0, and so on and so on. And so we come out with this network address right here, which just happens to be 192.168.15.0. The reason for the 0 is because, well, this right here is all zeros. 0 and anything is 0. So when we've converted everything over, it all works out in this way. So again, let's take that back one more time. So we take this address, 192.168.15.0, and we convert it into binary. We then do the same thing with the mask, 255.255.255.0, and we convert it into binary. We then AND these together. 1, 1 equals 1, 1 and 1 equals 1, 0 and 1 equals 0, and so on and so forth. Pretty much what we're doing here, everywhere we have 1s, we're copying the address down. You'll notice that's exactly the same. And then anywhere in the mask that there's a 0, well, the answer for the network is 0. So we've taken the decimal numbers for the octets, we've converted them to binary. We AND them in binary, and then we convert them back to decimal numbers so that we as humans can read them and understand them. So if I see an address 192.168.15.42 with a mask of 255.255.255.0, and somebody asks me, what is the network address? Well, the network address is 192.168.15.0. That's how we would AND that together in order to come up with the network address. Great. Well, if that is the network address, then what is the host address? Well, the host address is this part right here. It's what's left over. It's everything that wasn't part of the network address. And in this case, the binary then converts back into 42. And so now we can see, we can take an address and a mask, and we can use that mask to break the address up into two different pieces, a network piece and a host piece. This will come in handy as we start trying to figure out, is my computer on the same network as another computer? Okay, so now that we know the purpose of a subnet mask, we know how these work. Now we can start getting into how a classless interdomain routing works. And what it does is it allows for networks of any size, literally any size from 2 to 16 million hosts. And there's two different ways that we can write this. For instance, if we have the address 192.168.15.0, we can then give it a mask, 255.255.255.128. That's going to be a new one to you. Or with a CIDR notation, 192.168.15/25. Those are both exactly the same thing. They mean the same thing. The 255.255.255.128 is equal to a /25 for the CIDR notation. Exactly the same thing. One is just possibly easier to write than the other, while the other one is easier to possibly understand at this point. But this means that we can have different sized networks. So for instance, if I choose a /23, then that means I have 512 addresses available for my network. If I create a network with a /24, 256 addresses. /25, 128 addresses, and a /26 for 64 addresses. And I can keep going all the way down to a 30, which gives me my 2 addresses, or all the way up to 8 or even less, which gives me my 16 million or even more addresses. Okay, so as we're talking about this, there is a difference between usable hosts and usable addresses versus total addresses. And this is important to throw in here as we're talking about these address sizes. In every single network, there are 2 addresses which are unusable. The very first address in a network is referred to as a network address. So for instance, if I had a network 192.168.42.0/24. Now this would traditionally be a class C network with a subnet mask of 255.255.255.0. Now the very first address here is in fact 192.168.42.0. That is my network address. And so as I'm documenting this, as I'm documenting out my network diagrams, and I'm saying this network's over here, this network's over here, this is how I would refer to it. I would say this network is the 192.168.42.0 network. Every single host on that network identifies themselves as belonging to the 192.168.42.0 network. Because this is a unique term that's used in the environment, I just can't assign a host to the .0 address. So the very first address I can actually assign to a host is going to be .1, 42.1. So the very last address, 192.168.42.255. Oops, 255 is referred to as the broadcast address. Now, the broadcast address is, again, it's a unique address. It has a very special need, a very special purpose. And in this case, the broadcast address, well, a broadcast is a way of talking to everybody on your network. Think somebody standing up in a room and screaming out really loud, and everybody has to listen to him. Going into a crowd with a megaphone and speaking really loud, everybody hears him. He's broadcasting his words, and everybody hears what he's saying. And that's exactly what it's used for in the computer realm as well, is for a computer to talk to everybody else that's on his network. Because of this, because this is a broadcast address, it is not accessible by anybody else on that network, or not assignable to anybody else on the network. Therefore, any host on that network can have an address 192.168.42.1 through 254. They cannot have 0, they cannot have 256, only 1 through 254. Therefore, every time we look at an address, this 255, 255, 255.0, I do not have 256 usable addresses. I have 256 total, but only 254 usable. Okay, so let's work all this together and see exactly what this means in a real scenario. For instance, here I have an example of host number 1 has an IP address 192.168.124.163 and a subnet mask of 255.255.255.128. Host 2 has an IP address 192.167.124.110. Host 1 wants to talk to host 2. Is it on the same network? Are these guys on the same network? So that if host 1 wants to talk to host 2, can he talk directly? It's essentially saying, is he in the same room? Can he talk directly to them? Or does he have to go to a router or have somebody else be an intermediary to talk to them? Well, in order to figure this out, we take those numbers and we start off by converting them into binary. So make this a little bit bigger so we can see it. Perfect. Okay, so I'm going to start off with the first host. First thing I'm going to do is I'm going to convert my addresses here into binary. So 192.167.124.136 is 11000000 dot 01000011 dot 01111100 dot 1000. Yeah, 1000. Great. And then the subnet mask, well, this one's really easy. The first 3 of these guys are 255s, and if you recall from our binary discussions, 8 bits, which is what we're working with here, 8 binary bits, all ones equal 255. So that means the first 3 octets here are all ones. And because I already have a set of ones up above, I don't even have to look at them to see how many to type in. 128 into binary turns out to be 100000. And so I can now AND these guys together in order, not mask, in order to identify what its network is. So again, to AND these guys together, 1 and 1 equals 1, 1 and 1 equals 1, 0 and 1 equals 0, and so on and so forth. So I come out with, oops. Oops. Excuse my typos there. I come out with this. Now again, what I'm doing here, basically I'm looking at the subnet mask and I'm drawing a line here and I'm saying everything to this side of the mask is my network, and therefore everything up here is going to carry straight down into my network address, and then everything else is going to be just simply zeros. And once I've ANDed this together in binary, now I can convert it back into decimal, which means my network address is 192.67.124.128. All right, so there we go. For host number 1, I have my network address, 192.67.124.128. So now that I have host number 1's network, I know what network it's on. If I want to talk to somebody else, it either has to be on my same network, so I can take the same subnet mask and do the same process with it, or I have to send it to a router and have somebody else direct traffic to it. So I repeat the process for host number 2. Let's see, host number 2, 192.67.124.110. And in this case, I use the same subnet mask, so I'm just going to copy this right here and paste it on in. So again, I start off with converting my my network address, my IP address, into binary. Most of this is going to be exactly the same, so let's see if I can go through this fairly quickly. There we go. So this was a little bit quicker because I have, let's see right here, 192.168, sorry, 192.67.124 is the same as here, so I was able to essentially copy these first 3 octets. It was only the very last octet right here that I had to recalculate the binary for, which comes out right there. So again, same thing, because the first 3 octets are the same for the host address and the host address for the IP address for host 1 and for host 2. Well, I can essentially copy the first 3 octets of the network address from host 1 onto host 2. Just trying to make this a little bit easier on myself. The address, the ANDing still works through 1 and 1 equals 1, 1 and 1, 0 and 1, and so on and so forth all the way through here. And now I just have these remaining guys. 0 and 1 equals 0, 1 and 0 equals 0, 0, 0, 0. And now that I'm done ANDing everything together, I just simply convert it back into decimal. Okay, so now I can see host number 1. Host number 1 has a network address of 192.67.124.128, and host number 2 has a network address 192.67.124.0. Because they have 2 different networks, they are not on the same network. So the answer here is no. No, they are not on the same network. They cannot talk directly to each other. It's the equivalent of them not being in the same room together. Therefore, they cannot talk directly to each other. They have to have some sort of a go-between, which you'll learn in the future is referred to as a router, in order to direct the traffic from one network to another. So, with all this being said, we've talked about figuring out all these weird subnets. Basically, it comes down to, well, there's a whole lot of math that has to happen here, a whole lot of binary math, and it can get really confusing. But there's tricks in order to fix that, because it turns out we're not the first ones to do it. It turns out they've been actually doing this for years, and people have come up with cheat sheets. They've come up with ways in order to work with things easier for us to remember and understand. So what I did was I simply Googled CIDR cheat sheet. There we go. CIDR cheat sheet. And it came up with this information right here. There's a million of these out there on the internet, and I encourage you to write down most of this information and memorize it. It is a great way to be able to remember all this, especially if you have to go take a test. You memorize this. You go in to take the test. They give you a piece of scratch paper, and what you do is you write this out right before the test starts, or as soon as the test starts. And then as you're going through working on the homework or on the assignment, you can immediately look and see, oh, I have a /27. How many usable IP addresses do I have? I just simply look it up right here. I have 30 usable IP addresses in a /27, and that has a subnet mask of 255.255.255.224. Okay, so what this means, if you remember, our IP addresses are 8 bits, 4 8 bits, 4 octets. There we go. 4 octets. So 4 times 8 equals 32 bits total. Obviously, I can't have 32 bits assigned simply to networks, because then I would have no bits assigned to hosts. And therefore, the largest possible prefix I can have is a /31. In case that doesn't make sense. I have 32 total bits. If I put a /31, then that means 31 of them are assigned to the network and only one is assigned to my hosts. So what this means is my potential hosts, I have 2 potential hosts. Remember, binary, 1 bit gives me an on and an off, which is 2. So I have 2 potential hosts. However, I also have a network address and a broadcast address, which means usable, I have 0. But my network address would be 255.255.254. Okay, well, that was nice, but ultimately, because actual hosts here is 0, unusable, pointless. So the next largest network, or I guess smallest network I can have, is a /30 with a subnet mask of 255.255.255.252. I now have 2 bits. Remember, 32 bits total, 30 of them for the network, which means I have 2 bits for my hosts. 2 times 2 is 4, which means I have 4 potential hosts here. So 2 to the second, or 2 times 2. So 4 potential hosts. I have 2 addresses which are reserved, my broadcast address and my network address, which means usable, I have 2 addresses. This is a great network size if I want to connect, say, 2 buildings together, and I want to have one address on the router in building A and another address on the router in building B, and so now they can address each other and communicate back and forth. I only need 2 addresses in this network, therefore I can use a /30. Same thing as it goes as we go down here, /29. So 29 bits for the network, which means 3 bits for the host, which gives me 2 to the third, or 2 times 2 times 2. 8 potential hosts, minus 2 is 6 actual, and my subnet mask. So again, I would suggest you find one of these CIDR cheat sheets. I would specifically memorize the prefix, the actual hosts, and the net masks. You can remember the potential hosts and then just simply subtract 2. So minus 2 in order to get the actual hosts, in which case you only have to remember 3 sets of things. Probably the hardest thing right here is to remember the net masks, and again, if you forget these, well, you can figure them out on your own. Let's figure out how to do this. So one thing about net masks is they always start with ones on the left. So it's always, for instance, 1 1 1 1 1 1 1 1 dot, and then 0 0 0 0. The ones always come in from the left, which means we don't have to worry about all the possible net masks out there. We only have to worry about the ones with all ones on the left. So, assuming we're just dealing with the last octet, I'm gonna go from there. 1 2 3 4 1 2 3 4. So this is 255. If I then go in 1, 254. Again, I'm just simply doing binary to decimal. I've done this a million times, so I recognize these numbers right off the bat. 252. 248. Yes. Let's see, 1 1 1 1 0 0 0 0. 240. No. Yeah, 240. Now I have to look at my cheat sheet. Yes, 248, 240. Okay. $224, and so on and so forth. Now I can memorize this, or I can simply do the math. I can simply just see, well, you know what, here I have a different color here. Here I have my zeros essentially scrolling or moving in from the right to the left, so I can write all of this information out and then just convert, well, 8 ones is 255, 7 ones 254, and so on and so forth. And once I have this written out in binary, well, then I have this right here as well. It's kind of works together right there. Okay, so this introduction has gone a whole lot further than I necessarily expected. However, CIDR, classless interdomain routing, again, it came about because the classful routing that was originally designed was just super inefficient. And it turned out that people needed networks that supported 2 hosts, or 60-something hosts, or 1,000 hosts, or if I keep scrolling down on this cheat sheet, well, 4 billion? Maybe not quite 4 billion, but maybe 4 million. And so I can work this out to be able to be any size I might possibly want. And then I can use the subnet mask in order to determine if something is on the same network as me or not.